Hello class, this is CSE 4600, Section 1, Week 8, Spring 2025. Alright, so in case you missed it, I'm gonna go over the answers for the first set of memory problems. So, problem 1, consider a swapping system where there are the following holes in memory: 10, 4, 20, 18, 7, 9, and 15 megabytes, and there are requests for memory segments of the following sizes in the following order: 12, 10, and 9. Let's call them processes 1, 2, and 3. And the question is, which holes are taken by which processes? So, under first fit is find the first hole that is large enough to hold a process. So, by that logic, process 1 goes in the 20 megabyte hole, process 2 goes in the 10 megabyte hole, and process 3 goes in the 18 megabyte hole because the 20 megabyte hole was already taken. Also keep in mind that these processes, when they go in the holes, they leave behind smaller holes. So when process 1 went into the 20 megabyte hole, it left behind an 8 megabyte hole. Process 2 left no such hole behind because it perfectly fit. Process 3 left behind a 9 megabyte hole when it went into the 18 megabyte hole. So that is first fit. Best fit is find the hole that is just large enough to fit a process. So process 1, that's 12 megabytes, goes in the 15 megabyte hole because that is the process that is just large enough. There weren't any processes that were 12 megabytes, so we went with the next best thing, which is the 15 megabyte process. Process 2 was 10 megabytes. It goes in the 10 megabyte hole again, because, well, that's the exact size that we needed. Process 3 goes in the 9 megabyte hole, because, well, again, perfectly sized. Worst fit is where we find the largest hole available and just put the process in that hole. This is going to leave behind a leftover hole. So, under worst fit, we put the 12 megabyte process into the 20 megabyte hole. So process 1 goes in the 20 megabyte hole. The next process is 10 megabytes in size, and the next available hole is 18 megabytes. And process 3 goes in the next available hole after that, which is 15 megabytes. And all of these leave behind different size holes. So process 1 left behind an 8 megabyte hole, process 2 left behind another 8 megabyte hole, and process 3 left behind a 6 megabyte hole. Okay, next fit is a variation of first fit, where we don't start over from the beginning. We start where we had left off from when we made a previous request for memory. So if we just start at the beginning and just go down the list, and when we reach the end we go back to the beginning. Let's start with process 1. Process 1 is a 12 megabyte request for memory. So we find the first process that will hold that entire process. We find the first hole that will hold that process. That was the 20 megabyte hole. So that is our starting point for when we find the next hole available for process 2. So we start at the 20 megabyte hole, which is now an 8 megabyte hole because it left behind a hole. Process 2 goes in the 18 megabyte hole because that was the next one after the 20 megabyte hole. That leaves behind a hole. That's 8 megabytes, which is obviously much large enough for our next process, process 3. So we just go down the list from that point. 7, not large enough. 9, oh yeah, that's large enough. So process 3 goes in the 9 megabyte hole. When I grade your memory problems, I'm going to grade them based on completeness. So don't worry if you have like 1 or 2 entries just a little bit off. When I grade these by completeness, I'm just going to make sure that you're mostly correct. And if you are, you're basically good to go on that front. Number 2. In the figure above, the base and limit registers have the same value of 16384. Is this a coincidence? Yes, it is. So, a system that uses a base and limit register to ensure each process has its own memory space must be able, it should be able to load any process of any size in any location in memory. So it's a coincidence that the two registers happen to have the same value. So that's not untested. Number 3. A swapping system takes 4 nanoseconds to read or write a 32-bit memory word. Assuming holes and memory segments are randomly distributed, how long would it take to compact 4 gigabytes of memory? For clarity, by gigabyte we mean 2 to the 30th bytes, which is actually a gigabyte. Don't worry about it. I talked about this mismatch in the beginning of the class, so let's just say 2 to the 30th bytes and not 10 to the 9th bytes. 1 byte is 8 bits, 1 nanosecond is 10 to the negative 9th seconds, and transferring a 32-bit word takes 2 operations. 1 read operation, which takes 4 nanoseconds, and 1 write operation, which takes another 4 nanoseconds. So, unit cancellation is weird, says Randall Monroe. He previously said that when he tried to calculate the time it takes for a bird to poop in your mouth. Anyway. It takes 4 nanoseconds to read 32 bits, but it takes another 4 nanoseconds to write 32 bits. So, the first two terms here is simply 2 times 4 nanoseconds over 32 bits. Our next term here is 32 bits over 4 bytes, because 1 byte is 8 bits. We have 4 gigabytes, which is our next term, and we have 2 to the 30th bytes per 1 gigabyte. Again, it should really be gigabyte, but whatever, we're stuck with this. And it's sometimes annoying. So 4 gigabytes times 2 to the 30th bytes over 1 gigabyte. And then 10 to the minus 9 seconds over 1 nanosecond. So, we can stare at this calculation here and figure out which terms to cancel out. So, I'll just draw the terms that we're canceling out. Bytes canceled out. Gigabyte canceled out. Bits canceled out. Nanoseconds canceled out. So, our time is going to be in seconds. We can do some further canceling out by canceling out this 32, 4, and there's another 4 over here, but that is not canceled out. So we have 8 times 2 to the 30th power divided by 10 to the 9th. So we can rearrange this further. That 10 to the minus 9th in the numerator is equivalent to 10 to the 9th in the denominator. So it is 2 times 4 times 2 to the 30th power, all divided by 10 to the 9th power. And if we do the math by just punching them all into a calculator, we get about 8.5 seconds. A little over 8.5 seconds. So that assumes by 32... So that assumes by gigabyte we mean transferring one group of 8 bits. If we were working with like 2 to the 32nd power 32-bit words, then that answer would be, well, 4 times that, because we were working with 8-bit words, not 32-bit words. So if by 4 gigabytes we meant 2 to the 32nd power 32-bit words, and not 2 to the 32nd power 8-bit words, we would get an answer that's 4 times this. But if we just interpret it as follows, then we get an answer of around 8.59 seconds. Unit cancellation is weird, and interpretation of units is even weirder. And I say this having dealt with situations where people would misinterpret gigabyte to mean 10 to the 9th instead of 2 to the 30th. I see this discrepancy a lot, and that's why I talk about being clear with our units, even if we are using the words in the wrong way. So when I say gigabyte, I really mean 2 to the 30th bytes, even though there's a word for that that is nowhere to be seen in the book. Okay, so those are the answers to the 3 problems, and I do have another set of problems for you, but the idea right now is we would just work on this set of problems together in class, so that way I don't have to stress you out with having for you a project to be done over spring break. Rather, I'll have the project details posted, but I won't have the project due until, say, the tail end of week 11 or the beginning of week 12. So, the memory problems are as follows. So this is your second set of memory problems. Problem 1. What's the difference between what's the difference between a virtual address and a physical address? Number 2. If it takes 1 nanosecond to read an instruction and an additional n nanoseconds to service a page fault, if on average a page fault occurs every k instructions, what is the effective time of reading 1 instruction? Write this out as a formula. So that is another problem from the book, but I added an extra problem, and that is to use this formula. What would happen if a page fault occurred every 10 instructions on average, and servicing a page fault added an additional 1 million nanoseconds? And then what if instead page faults occurred every 1,000 instructions on average? We are working with averages here because in practice, it's gonna get really messy really fast. The only way you would ever get a more accurate number is to just simulate the whole program and see how many page faults you get. We work with averages, in this case, just for practice, even though reality is often complicated. Number 3. Using this diagram, convert the following addresses here from virtual addresses to the corresponding physical addresses. So I will give you a bit of a hint. Because we know the page size is 4096 bytes. To convert these addresses from virtual address to physical address, divide that address by 4096 bytes. The answer you get, round that down, and the remainder you get, that is your offset. The answer you get from dividing, convert that page number into the corresponding frame number. Multiply that frame number by the size of your page, and then add that back to your offset. That is how you convert a virtual address into a physical address. And there is a little bit of a freebie if you look closely in the table. Look at page 1. It's loaded in frame 1. So if we have 4K pages, which are 4096 bytes, and we have virtual address 4100, if we subtract 4096 from 4100, we get offset 4 page 1. So page 1 offset 4. So virtual address 4100 is page 1 offset 4. We look at where page 1 is loaded in physical memory, and it is loaded in frame 1. So frame 1, we multiply the frame number by the size of the page, and we get 4096. We add that back to our offset, which was 4, and then we get physical address 4100. I told you it was a freebie. We didn't even have to convert anything. So if the page number is coincidentally the same as the frame number, we don't have to convert anything. But that assumes that we only have just the one program in memory. And in practice, there would be multiple programs loaded into memory. So every program is gonna have a page 1. But it would be such a amazing coincidence if program 1 had page 1 loaded into frame 1. Anyway, you'll be converting these addresses, and I added an extra address. So this is actually an extra address that was never in the book. So I want you to see what happens if you try to convert this one. So the trick here is to realize that by 4K, we don't mean 4000, we mean 4096. Again, with that discrepancy of powers, working with powers of 10 versus powers of 2. We say that to the 10th power is approximately 10 to the 3rd power, but I say approximately because it's approximately. There's that discrepancy that only builds up more the larger a power of 2 we go, and that's why I make a big deal about being clear with what our units are, particularly with this problem here. What do we mean by gigabyte? I don't mean 10 to the 9th bytes, I mean 2 to the 30th bytes. Even though that's the wrong term, but here we are. Anyway, I'll be uploading these instructions for you to try out, and on Tuesday, we're gonna try them out, and on the following Thursday, I'll give you your instructions for your project number 2, and we'll talk more about your project 2 when we come back from spring break. By the way, due to a family thing, I am going to have week 10, our Tuesday meeting, be online. So I might just end up recording that on request, and then uploading it privately so you can see it in case you end up missing it, okay? Alright. So, that is everything in regards to your memory homework. Now, hold on. Let's recap what we were doing last Tuesday. So, there was one example from a different textbook that I just wanted to show you because it was just really hands-on. So, let's recap on what that was, and yeah, so there is a different textbook being used that is Operating System Concepts 10th edition by Silberschacht and Company. We are using Modern Operating System by Andrew S. Tannenbaum and Herbert Bose. I like to call this the dinosaur book for obvious reasons, and this the carnival book for obvious reasons. So I took the example from the dinosaur book because I just liked it more than what was in the carnival book. And that is the idea of a reference string. It's a string of page numbers that corresponds to what page are we looking at the moment. So, as a program runs, it's going to generate memory addresses. It's going to generate memory addresses, and it might look something like this. So, we have this sequence of memory addresses, and if we pretend that these addresses are for a decimal computer, and the upper 2 digits are the page number and the lower 2 digits are the offset, then what we can do is convert this string of addresses 0100, 0432, 0101, 0612, 0102, 0103, 0104, 0101, 0611, 0102, 0103, and chop off the last 2 digits on everything, and then remove all duplicates, all consecutive duplicates. So if we just chop off the last 2 digits of all of these addresses, we'll be left with the page numbers. But we'll also have, for example, a string of consecutive page numbers that are all the same. So 0102, 0103, 0104, 0101, that is the same page being accessed each time. So instead of counting that as 4 instances of accessing one page, we count that as 1 instance of accessing the same page. Under the following reasoning that if the first time we try to read from this page, that page was not in memory, the moment we load it into memory after serving that page fault, we don't have to load it again. So, the first time you read a page, any successive accesses won't incur any more page faults. So if page 1 was not loaded when we try to read it here, it's going to be loaded when we try to read it again, and again, and again. But it might not be loaded the next time we reread it, when we get to this instance of reading page 1 here. So when we condense down our reference string like this, we have this much shorter sequence of page numbers. What we're doing here is counting how many page faults occur. And we're going to do that by using this reference string. We are making one other assumption here, and that is, when we load a program, none of the pages are loaded into memory. So the moment we try to read a page, it's going to page fault immediately. But that's okay. If a page fault occurs, it means the operating system stops what it's doing and loads that missing page. It might, in the meantime, run some other program in the meantime. Anyway, we are assuming something called demand paging, where at the beginning, none of a process's pages are loaded into memory, and they are only loaded when demanded by a process. So think of what would happen if we only had one page frame available. We can only hold one page at a time. If we only had one page, it wouldn't matter which algorithm we would use. We would have a page fault every time we tried to access a new page. I'm reading page 7, page fault because it's not there. And now I want to read page 0, page fault because it's not there. Page 7 is there, but I have to take it out to make room for page 0. Now I need to read page 1, page fault because page 1 isn't there and I have to get rid of page 0. Read page 2, page fault because now page 2 I don't have it and I need to get rid of page 1. Page 0, I need to read that. Page fault, because I don't have page 0 and I have to get rid of page 2. This is what happens if we don't have enough page frames available for a process. So the reasoning is, if we add more page frames, if we give a process more page frames available, then we would have fewer page faults. In the extreme, we would have a page frame for every page. Therefore, once every page is loaded, we will never have page faults again. So what are the unique pages in this sequence of pages? 0, 1, 2, 3, 4, and then 7. That is all. 5, 6 frames needed to store all the pages we ever need. So we load page 7, we load page 0, we load page 1, we load page 2. We access page 0 as an issue because it's already loaded. We load page 3, load page 0, but that's already loaded. Load page 4. At that point, we have seen all the pages we will ever see in this program. We will never have another page fault. So, we will be investigating what happens with this string here using optimal page replacement, FIFO page replacement, and least recently used page replacement. We're going to use 3 page frames, 1 page per frame. The first one is so good that we can't implement it in practice because it requires future knowledge of what will happen in the future. If we have a sequence of memory addresses, we can determine which pages will be referenced. We have our reference string, so we know which pages will be referenced in the future. When we reference a page, it might be referenced later, say a few instructions from now, or maybe a few thousand instructions from now, or it might be the last time we'll ever see this page again. in practice, we don't know whether a page we access will be the last time we'll ever access it. But under optimal page replacement, we assume we have all that information. And if we have information about the future, then we can see what would happen then we can determine what would happen under the best possible conditions. When we read the first 3 pages, we read page 7, that's a page fault because it's not there. We read page 0, that's a page fault because it's not there. We read page 1, that's a page fault because it's not there. So, right off the bat, we have 3 page faults. When we read page 2, we don't have room for page 2. All of our 3 page frames are taken up, so we determine which page to remove to make room for page 2. We select the page that won't be used for the longest amount of time. That is the rule for optimal page replacement. You start here, and you determine which of the 3 pages, 7, 0, or 1, will occur the last. From page 2, we know we're going to see page 0 again. From page 2, we know we're also going to see page 1 again, but that won't be for several more page references. But the same is true for when we access page 7, but look, that's even further ahead. So, page 7 is the best candidate for replacement. So we remove page 7 from our page frame, and we put page 2 in its place. We continue with this process, select a page that won't be used for the longest amount of time, but only if we encounter a page that isn't loaded into a page frame. We're now reading page 0, but that was already in a page frame. No problems there. But we do need to read page 3 next, but we don't have room for that. So, we previously had pages 2, 0, and 1 loaded in our frames, but now we need to make a decision about which page to remove. So is it page 2, 0, or 1 that we remove from a page frame? Well, the answer is 1, but how is the answer 1? Well, are we going to see page 2 again? Yes, we are. Like 1, 2, 3 instructions from now. Are we going to see page 0 again? Yeah, right away. Are we going to see page 1 again? Yes, we are. But that won't be for a while. So, we take out page 1 from a page frame and place page 3. We do this again and again. So, with pages 2, 0, 3 loaded, and we want to read page 4, we're going to see page 2, 0, and 3 immediately after reading page 4. But of those, page 0 will be used after pages 2 and 3. So, we can take out page 0 and put page 4 in its place. And then we keep going and going. The end result is OPT, results in 9 page faults. But as I said, we can't implement this in practice because we have no means of looking into the future. But it is great for benchmarking purposes because if we know OPT ran with, say, 9,000 page faults, we use this as a benchmark for improvement. If another algorithm ran with 9,100 page faults, then it might not be worth finding a better algorithm. If a different algorithm yields 23,000 page faults, then there's room for improvement. First in, first out page replacement. So we have first in, first out as a CPU scheduling algorithm, and now we have first in, first out page replacement algorithm. So we have our pages fall in line in a queue, and the oldest page is the first one to be replaced. So when we read pages 7, 0, and 1, they get loaded into the queue. So the thing is, we need to read this queue from right to left. So 1 was the most recent page, 7 was the oldest page to be loaded. So, start of the queue is on the right, end of the queue is on the left. When we read page 2, and we don't have page 2 in our queue, we pop page 7 and push page 2. So now we have pages 0, 1, and 2 in our queue. Now we want to read page 0, but we already have page 0. Now we want to read page 3. We don't have page 3. We pop page 0 from the end, push page 3 at the beginning. Okay, but now we need page 0 again. So we have to pop that last page, which is page 1, and push page 0 at the beginning. Hey, wait a minute. Didn't we just use page 0 already? Yes, we did. We used page 0 previously, popped it from the end of the queue, only to have to push it back at the beginning of the queue. And that's the problem with FIFO page replacement. You might have a page that is frequently being accessed, and if you have such a page, under FIFO, it's gonna be popped only for us to have to push it back at the beginning, right after. And that is a problem with FIFO page replacement. Frequently used pages are paged out and in more frequently than they need to be. We continue this process of pushing and popping pages, and here we have 15 page faults. With OPT we had 9, with FIFO we have 15, which is not that great, because out of 15 page faults out of a reference string of size 20, that's still quite a lot. But then again, it could be the case that we are, because the reference string here is only keeping track of what pages we're referencing. It doesn't keep track of what addresses are addressing. We could be accessing addresses on page 7 like 1,000 times in a row, and then read from page 0 only like once. What this experiment does not do is keep track of how many times we access the same page. It's just counting the number of times, it's just counting the number of page faults. So if we access one page, and then access the same page like 1,000 times, there's still only one page fault. You don't get a page fault from accessing a page that you already have loaded into memory. You only get a page fault when you try to read it for the first time. The advantage of FIFO, though, is that it's easy to understand, but the performance, as I said, is not good. As I said, it's possible that you'll have a page that is accessed frequently, but with FIFO page replacement, you're gonna have that page be popped and pushed frequently. The downside of having these page faults occur so frequently is that the program slows down. The only bad thing that happens from a page fault is the program slowing down, which isn't bad, but it can slow down the program to a degree that it's unacceptable. So, what we want is to get our page fault rate, or rather the number of page faults that we get. We need to get that as low as we can. As low as we reasonably can with whatever algorithms we can conjure up. The next one is called LRU, and we have a stacked like data structure. It's not a stack in the sense of a stacked data structure. It's technically a linked list where if we have some entry that we're accessed that isn't at the top, we move to the top. If a page being referenced isn't in the stack, we remove the page that's at the bottom of the stack and then add the new page to the top. What this algorithm is doing is update this stack-like data structure every time we access a new page, which turns out to not be cheap because we need to update this stack data structure every time we access a page. But that's the problem with LRU. we have a data structure that is expensive to update, but maybe we can cheat a little and find some other algorithm that will approximate this behavior. As I said, technically this is not a stack. It's actually a linked list where if we are trying to read a page that isn't at the top, we move it to the top. This behavior of reading stuff in the middle and then moving it to the top naturally moves the most frequently used pages towards the top and the least used pages towards the bottom. And as I said, implementing this is not cheap because you need to update this every time you do a page reference. I'm gonna call it a stack anyway. So, we have pages 7, 0, and 1 being read. We have 3 page faults, and they are loaded from bottom to top, 7, 0, 1. When you read page 2, we push page 2 to the beginning and pop page 7 from the end. When we have page 0 to be read next, we have page 0 at the bottom, but all we gotta do is just move it to the top. That's it. And now we have updated this data structure, so it says that page 0 is the most recently accessed page. Least recently used keeps track of which page is at the bottom. Least recently used, the least recently used page at the moment is page 1. So that means when we go ahead and read from page 3, we don't have page 3, we pop page 1, push page 3. And now we have to read page 0 next. We just move that to the top of the stack. And now we have from bottom to top pages 2, 3, and 0. And now we want to read page 4. Because page 2 is now the least recently used page, we pop that, push page 4 to the top. But now we need page 2 again. Page 3 is the least recently used page because it's at the bottom. We pop page 3, push page 2. And we continue with this process until we reach the end of our reference string. We get 12 page faults here. Not good as OPT, but still better than FIFA. So the rest of the slides are going to be talking about other page replacement algorithms, such as not recently used second chance, the clock algorithm, and an LRU approximating algorithm. We talked about the page table, and it had several bits that determined what happened to the page. The reference bit denotes whether a page has been read or written to since it was loaded. The modified or dirty bit denotes whether a page has been changed. If we make changes to a page, when we select that page to be replaced, we need to save those changes first. But if we have a page that has never been changed, or it's a read-only page, which is probably just as good, if not better. If we have a page that has never been changed or is read-only, when it comes time to replace that page, we don't need to write that back to the disk because there are no changes to make to the disk. What we can just do is overwrite that page with our new page. Due to the overhead of LRU and the inefficiencies of FIFO, many operating systems will use one of several different page replacement algorithms, and the textbook talks about 10 algorithms in total. Of those, we had optimal page replacement, FIFO page replacement, and LRU page replacement. The other ones are not recently used, second chance, and the clock algorithm, which are technically the same algorithm, but just implemented differently. And there's another one called aging and the working set algorithm. We're just going to look at 4 of these. So, not recently used. Suppose you have 4 pages loaded in memory, and initially they are untouched. There's also a timer that resets reference bits, say every 20 milliseconds. So we have pages 3, 1, 4, and 5. They are perfectly pristine, unmodified, and unreferenced. But we have a timer that resets their reference bits periodically. Before the 20 milliseconds have elapsed, all 4 pages will have been referenced, and 2 of them will have had changes made to them. So we see that pages 3 and 1 have been modified, and all 4 pages have been read. Remember, the reference bit asks the question, has this page been referenced? That is a read or a write. Modified denotes whether a page has been changed. So have we read any of these pages? Yes, we have. Have we written to any of these pages? Yes, we have. Pages 3 and 1. When that clock goes off, we reset all the reference bits for all of our pages. And let's just say during the next 20 milliseconds, 2 more pages are referenced. So what does this tell us? It means during the first 20 milliseconds of this program running, we had to read every page. And also had to write to 2 of the pages. During the next 20 milliseconds after that, we only had to use 2 pages. Which of these pages do we replace if we need to make room for a new page? That's the question now. So, let me back up. During the first 20 milliseconds of this program running, we read every page and wrote to 2 of those pages, pages 3 and 1. During the next 20 milliseconds, those reference bits are reset, and you now only read from 2 of those pages. If we need to replace a page because we need to load a new page, which page do we replace? Well, not recently used uses bit combinations. So we classify pages based on bit combos where a class 3 page has been referenced and modified. This is a page that is likely to be used frequently, and it's the worst choice for a replacement. You only choose a class 3 page if there are no other pages to choose from. Class 2 pages are pages that have been referenced but not modified. These are pages that are likely to be read frequently, also a bad choice for a replacement. Class 1 pages, these are pages that have not been referenced but they are modified. If we are to select such a page, there are changes that we need to make first. Because, remember, when we swap pages, they are moved from main memory to a backing store, which is an area on the hard disk drive. Whenever we have changes made to a page, we gotta save those changes before we move our desired page into that frame. So, class 1 pages are pages that have not been referenced but modified. So if we select a class 1 page, we need to do the extra step of saving all those changes to the disk. A class 0 page is a page that has not been referenced and has not been modified. It is an untouched page, or at least a page that has not been touched in a while. Class 0 pages are our best candidate for page replacement. A class 0 page has not been referenced and has not been modified. So, under not recently used, we pick out a class 0 page to replace. If we don't have any class 0 pages, then we try class 1 pages. If we don't have any of those, then we try class 2 pages. And if we don't have any of those, we replace a class 3 page. And that's the algorithm right there. So of those 4 pages, and I actually set it up so we have one of each page class. We have a page that has been modified but not referenced. We have a page that has been modified and referenced. We have a page that has not been modified but referenced. And now we have a page that has not been modified and has not been referenced. That's a class 0 page right there. That last one is a class 0 page. So that is the best page to replace if we need to make room for a new page. If we have two pages that fall within the same class, then we just use a tiebreaker strategy. Consider what would happen if instead, when the timer went off, all but page 3 was modified. That means, in this example, the only option is page 3, which is a class 1 page. The problem with swapping out a page that is class 1 is, as I said, we have to do that extra step of saving all those changes. Class 0 pages have no such complication. We just overwrite that page because because class 0 pages, the copy on the disk and the copy in the page frame, they're the same. We do not need to save any changes. When a page is loaded from the disk into memory, it isn't moved from the disk, but rather a copy of it is made and loaded into memory. When a page is selected for page replacement, whether a page is modified or not determines whether the copy on the disk is updated. So the copy of page 3 on the disk will not be up to date compared to the one in the page frame. So we gotta save those changes before we load our new page, say it's page 7, into the frame that page 3 was in. When a page is selected for replacement, if the page has no changes made to it, that is, its modified bit is 0, then the new page simply overwrites the existing page. If the page has had changes made to it, that is, its modified bit is 1, then we must page out the page before we have our new page overwrite it. So, remember that issue I talked about how FIFO replaces pages that we are currently using? So, previously, when we were working with FIFO, we would read a page that turns out to be a frequently used page it out, only to page it back in immediately after that. And that is the issue with FIFO, and we can fix it as follows. We use the reference bit. As before, when a page is referenced, its reference bit is set to 1, and a timer periodically resets these bits to 0. So this algorithm is a modification of FIFO. When a page fault occurs under normal FIFO, and in here we have page 3 at the back of the queue and page 7 at the front of the queue. Normally, that page 3, is the first to be removed. But now we have extra information in the form of the reference bit. If the reference bit is set, that is, the reference bit is 1. If that page has been referenced during that time interval, because that timer will reset every page's, we have a timer that will reset every page's reference bit. If that reference bit is set to 1, and it's at the back of the FIFO queue, and we need to do page replacement because we need to make room for a new page, what will happen is this. We take the page whose reference bit was 1 from the back, put it back to the front of the queue. We have given page 3 a second chance, hence the name second chance algorithm. We treat page 3 as a newly loaded page. If we have a page at the back of the queue with a reference bit set to 1, that page is likely to be a page that is frequently being used. So we move it to the front of the queue, reset its reference bit to 0. We've given that page a second chance. It doesn't have to be unloaded again. But we still need to make room for a new page. So, all we gotta do now is check the page at the back of the queue. Is the reference bit 0? If it is, then that becomes our page that we pop, and then we can push our new page at the beginning. So, under second chance algorithm, it's basically FIFO, but with the added change of if we are to pop a page from the back, but its reference bit is set, we push it back to the beginning, and we set its reference bit to 0. We replace a page that is at the back if its reference bit is 0. And that's a second chance algorithm. The clock algorithm is a different implementation of second chance. The implementation of second chance in the previous slides, it has the inefficiency of having to move pages from the back of the queue to the front. Instead of using a FIFO queue, we use a circular queue. And to visualize this, we can imagine arranging the circular queue around the clock, and the second hand goes tick, 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 tick. When it passes over a page, it resets that reference bit. So, the pointer hand, that indicates the page that we are to replace if we are to perform a page replacement. Say we want to replace page 3 with some other page, but its reference bit is 1. If that reference bit is 1, we set it back to 0 and we go to the next page. That pointer hand pointing to page 1, that is the page that we are going to replace because that reference bit is 0. If we need to load in a new page, we take out page 1 and then load in our new page in its place. In practice, few systems have the hardware necessary to implement true LRU. So we cheat and use different algorithms to approximate the performance of LRU. The first one of these is called not frequently used. Each page has a reference bit that is set to 1 whenever a page is accessed. We also have a reference counter. How many times has this page been referenced? A timer periodically goes off. When it does, if a page's reference bit is 1, that page's reference count is incremented by 1, and that page's reference bit is reset. After a while, each page's reference count will roughly reflect how much each page was used. And the page with the lowest reference count is the page that we replace if we need to replace a page. The problem with this algorithm is that it works too well. And that's because you might have a program that uses certain, say, pages 9 and 7 initially and never again. After some time, it might be the case that pages 9 and 7 are never used again, but their reference counts, they are still very high, 404 and 465, that the system still thinks that those are the most frequently used pages, when it could be, at that time, the program has stopped using those pages and now it's using some other set of pages. That is the problem of not frequently used. But there is actually a way to make this work. And one way to do that is to periodically divide the reference count by 2 each time. So, maybe there's another timer where the reference count is divided by 2, and then we round down accordingly. So over time, the reference count of all of these pages are going to decay exponentially. So even if we have a set of pages that have been frequently used in the beginning and never again after that, the reference counts are going to decay if we have some new set of pages that are frequently used. Then those pages will be the ones with the high reference count. And those 2 pages, pages 9 and 7, which have been used in the beginning and never again, eventually their reference counts will reach 0, and then they'll be prime candidates for replacement. There's another way to do this, and that is to use multiple reference bits. So say we have 4 reference bits. So if, say, I may just have to draw this out because I regrettably don't have a slide for this. So let's say we have 4 pages in memory, and each page has 4 reference bits. So we have 4 reference bits like this. And I'll just copy paste this. When we reference a page, the highest order bit is flipped. So initially all of these reference bits are 0, but the highest order one will be 1 if it's referenced, and all the other ones will be 0. Let's say that we reference page 3, we don't reference page 1, we do reference page 4, and we do reference page 5. Periodically, a timer will go off, and here's the trick. It's gonna shift these bit sequences. It'll shift the bit sequences to the right. So after that, the bit sequences will be as follows. And this is after 1 shift. I'll just copy that and doop, doop, doop. So, page 3 was referenced previously, but after a timer goes off, the bit sequences in these reference bits are shifted to the right. So instead of 1, 0, 0, 0, it's 0, 1, 0, 0. For this one, it's still 0, 0, 0, 0. For this one, it's 0, 1, 0, 0. And then for this one, it's 0, 1, 0, 0. Alright, so I'm just going to draw a crudely drawn clock to indicate that the bit sequences have been shifted. Okay, so now we have our new bit sequences. Let's just say after some time, we're going to be reading or referencing some other set of pages. So let's just say we still keep on reading page 3. So that is going to flip the highest order bit from 0 to 1. And now we have 1, 1, 0, 0 for the bit sequence for page 3. Let's say we now read page 1 as well. So we'll just draw this. And now it's 1, 0, 0, 0. We don't read page 4 anymore. So it stays at 0, 1, 0, 0. But we do read page 5 again. So that is 1, 1, 0, 0. And then the timer goes off again. So I'll just put these bit sequences at the bottom, and I'll copy the clock. When that clock goes off again, it's going to shift all the bit sequences to the right. So this 1, 1, 0, 0 becomes 0, 1, 1, 0. This 1, 0, 0, 0 becomes 0, 1, 0, 0. And so does this one. And so does this one. 0, 1, 1, 0. You see where this is going? Not yet? Okay. So let's just say after one more round of bit sequences being changed, we have, say, okay, so let's say we have one more round of pages being referenced. We access page 1 again. We don't access page. Okay, so page 3 is accessed again. Page 1 is no longer accessed again. Page 4 is accessed again. So that would be 1100. And then page 5 is no longer accessed again. So I'll just... 0110. Okay, so here is the trick. These bit sequences, interpret them as unsigned binary numbers. So this bit sequence, that is 8 plus 4 plus 2, that is 12. This one is 4. This one is 8. Oh, my bad. This should be 14. Because 111 is 7, and shifting that up and down is 7 multiplied by some power of 2. This is 4. This one is 12. And this one is 6. So here's the trick. If we need to replace a page where we allow for these reference bits to shift periodically, the page with the bit sequence that corresponds to the lowest unsigned binary number is the page that gets replaced. In this case, it's going to be page 1 because 1, 2, 4, 8. No 1s, no 2s, 1, 4, no 8s. This is 6, so that is no 1s, 1, 2, 1, 4, and no 8s. This is 12 because no 1s, no 2s, 1, 4, and then 1, 8. And this is 14 because no 1s, 1, 2, 1, 4, 1, 8. So that is 2 plus 4 plus 8. That is 12 plus 2, which is 14. That means page 1 is the page that gets replaced if we need to select the page for page replacement. So that is the trick. So this is a modification to not frequently used that's called aging. Or in the carnival, or in the dinosaur book, it's referred to using multiple reference bits and then shifting all the bits to the right. And this is yet another technique in which we can approximate LRU. Because remember, the problem with LRU is we have a data structure that we have to update every time we access a page. If we reduce the rate at which we need to do updates, say we have a clock that goes off, say, some number of milliseconds instead. If we have that clock, we do fewer updates. We don't get an algorithm that works exactly like LRU, but we get something that behaves close enough to LRU that it is worth implementing as a page replacement algorithm. So, FIFO has issues, LRU has issues, OPT has issues. In practice, we use something that is a modification or an approximation of FIFO and LRU. We can't use OPT in practice because we need a crystal ball for that. So, that is probably all the page replacement algorithms that I have to talk about. The rest of Chapter 3 is design issues for paging systems and local versus global allocation policies. So, maybe I'll just briefly describe what they are, and hope that whoever teaches CSE-4600 to you will get to this in greater detail. So, local versus global. Local page replacement versus global page replacement. So local versus global page replacement. That has to do with whether page frames are allowed to be taken from other processes. So, under local page replacement, if a process is allocated some number of page frames, it only has those page frames to work with. So if it runs out of page frames to work with, it must replace a page in one of its frames. If we have global page replacement, then we have the possibility of processes taking page frames from other processes. Which again, may be a thing that happens. Another thing to keep in mind is if we have multiple processes loaded in a computer, how many frames do we give to each process? One way is to give the same number of page frames to every process, which might not be the best option if it turns out that some processes need more page frames. So an alternative to equal page frame allocation is proportional allocation, where, depending on the size of the program loaded in memory, we give a appropriate amount based on how big that process is. So if we have 100 page frames to spare, and there are like 5 different processes of all different sizes, whichever process is the largest gets the largest share of page frames. Other considerations include, how big do we make the pages? So we were working with 4 kilobyte pages. The one thing about the page size and the page table is as follows. If we have smaller pages, that means the page table has more entries in it because there are just more pages to keep track of. If we instead have larger pages, then we don't need to make the page table as large. The problem with that is this. If we have large page sizes, we make the page table smaller, so the page table takes less memory. But we get more internal fragmentation, because if a process uses, say, half a page, half of an 8 kilobyte page, then that's 4 kilobytes that is unused. We can't use it anymore. But if we were instead allocating pages that are 4 kilobytes in size, then that last page will be completely full, and we don't need to give it another page. Unless it's a scenario where we have one word that continues on the next page. In that case, we would have to allocate a new page just to hold one more word. Just one more word, bro. And that is a design consideration when it comes to the page table and the page size and internal fragmentation. The larger the pages, the fewer pages that the page table needs to keep track of, the less memory the page table uses, but the more internal fragmentation we have. Conversely, smaller pages, more memory needed for the page table, but we get less internal fragmentation. And that is before I get to even more advanced stuff, such as what it looks like when pages are shared between multiple processes. Basically, when you have shared libraries, for example. So I think I'm going to have to save that for when you get to CSE-4600. Whoever teaches that will have to probably talk to you about that. So yeah, we went through quite a lot regarding memory, and that wasn't even all of it. There's still more that can be discussed, but if CSE-4600 is the basics and CSE-4610 is the advanced stuff, then I think I'll have to save that for when you eventually get to 4610, whoever that instructor may be. Okay? Alright, so that's going to be it on our discussion on these other page replacement algorithms. And yeah, I'm going to be uploading this new set of memory problems to you. I'll hand them out to you, but the idea is that we can do these together in class. So that way, when we come back from spring break, we should hopefully be in the mindset of embarking on our next project, even though I will be giving out the instructions for that sometime before. Just so we have it there and available, okay? Okay, alright. That's gonna be it for this video, and we'll come back over Zoom next week, alright? Alright, have a good one. Bye.